All right, so what I want to do today is talk a bit more about the basics of exponential function construction. So kind of starting with what you've already done, and we were talking about earlier parts of this. This is Module 4, Investigation 3, that I have the end of up right now. We talked about some of the earlier parts of that on Thursday. I want to talk about this just to kind of see what we do from tables and how we can write these exponential functions from tables of values like these. But then I want to do a more kind of detailed comparison of types of given information and how you write functions. Linear, constant rate of change, versus exponential, constant multiplicative change. So we're going to go through that. We are going to have a quiz that we'll work on the second part of class today that covers some of these things. It's in iMath. But in any case, to start with, let me make this a little bit bigger. Maybe. It doesn't want to be bigger, apparently. It only wants to be smaller. Well, let me try that again then. I'll reset it this way. All right, so when we're dealing with exponential functions, if we're trying to write a function, we need to have some sort of initial value and a way that we change away from that initial value, which is the same as with linear functions. We have some place to start and then a way to change away from that starting point, although it's usually like y-intercept and slope. And with exponential functions, we don't call it, it's certainly not slope, and we might not call it y-intercept, but it is in the way that we've used it a lot of the times. But some sort of starting position, some sort of starting value, and how we change from that by multiplying. So this question 7 through 10 asks you to do 4 different things. Find the ratio of output values, a 1 unit percent change, find the value at 0 for number 8 there, where it doesn't tell you, and write a function formula. So in number 7, I've got a function that goes through 0, 1, 2, 3, x values, and we have the corresponding y values, or output values, 16, 4, 1, 0.25. So just looking at those, this is easier than looking at the next one. If I were to say, well, what is it that I'm multiplying by to get from one value to the next to the next? You can probably see what that number is. You might think of it as dividing since it's getting smaller, but it's a relatively normal sort of number. What could I multiply by in number 7 to get from 16 to 4 to 1 to 0.25, aka 1/4? What could I multiply by? Yeah, multiply by 0.25, or 1/4. And so if I were going to, I'm going to just pull up a document. That's the document we're going to use later. If I have this function here, and let me shrink. There we go. If I wanted to write like what's going on in this, say, well, what happens with my y values? How do I calculate f of x values? Well, I start with, let's see if I can get to this. Is it gonna come on, man. I don't want to have to go to the weird one. All right, I'm going to start at 16, right? F of x starts out being 16. And then I vary away from 16 by repeatedly multiplying by 0.25. If I do it once, I get the value at x equals 1. If I multiply by 0.25 a second time, I'll get the value when x equals 2, 3 times to get the value when x equals 3, and so forth. So I just need to make this an exponent. Nope, that's not the button I need. I need to be able to see more of this. There we go. Nope, not fractions. This one. 0.25 to the x power. And sorry, let me make this a little bit bigger. hoping to not do it that way, but all right, so I have a starting value and I have a how I change away from that starting value. And since it's repeated multiplication, multiply over and over and over again, I have this what I multiply by raised to a power to indicate how many times I'm multiplying by that. And since we had 0, 1, 2, 3 as the x values in the table, and they're also nice numbers, it's maybe not too hard to see how this fits with that. But in terms of interpreting this, when we're looking at this like, oh, it's divide by 4 each time, or each time I look at a number in the table, it's like I multiply by 0.25, I'm finding 25% over and over again. If we wanted to put that back into the words of how lots of times story problems are phrased, this was like starting at 16, and is this function value increasing or decreasing as we go across f of x? As x increases, f of x, the output value increases or decreases? Decreases. And how they're normally phrased is, for these sorts of things, is decreases by something or another percent. Is it decreasing by 25%? No, it is not. And that's the weird stuff about exponential functions. When you're phrasing them in terms of percent change, with decreases, you don't, this is tracking how much is there, not how much has decreased. So this function f of x shows us how much is there. And each time x increases by 1, f of x is going to be only 25% of what it used to be, which means what percent did it decrease by? 75%. So when we're dealing with these decreasing functions, just phrasing-wise, if you're describing what percent change it is, it's going to be the complementary percentage to what you see there. It's how much smaller this is than 1. So it's 0.75 smaller than 1. 0.75 corresponds to 75%. So, and why I said it that way, how much smaller it is than 1. Sometimes it gets a little confusing, like, wait, do I subtract 1? Do I add, like, what am I, there's something about weird stuff. Sometimes I just ignore ones that are in there. If you're looking at a function that's in this exponential format, which sometimes is sort of like a times b to the x, kind of a generic format, you want to know how far that b is away from 1. If that base of the exponent was exactly a 1, this would be a constant function, because 1 to any power is just going to be 1. So if I had 16 times 1 to the x, that's just 16 all the time. If I have 16 times something to the x, and that something's less than 1 like this, that's a shrinking equation, and how much it's shrinking or how much it's decreasing depends on how much smaller than 1 that number is. On the other hand, if I have a number that's larger than 1, whether it's a little bit like 1.03, or maybe it's actually like 17 to the x power, which would be a huge increase, normally probably not stated as a percent change because that's crazy looking. But regardless, if it's something larger than 1, I want to know how much larger than 1 to know what that percent increase is. So the percent change is how far away that base of the exponent is from 1. The multiplication by 1 is like 100%, I'm keeping 100% of my value. If I have something smaller than 1, like 0.8, I'm keeping 80% of my value. 0.25, I'm keeping 25% of my value. So what's gone is how far away it is from 1. If it's larger, like 1.05, oh, I'm getting an extra 5%, 0.05, onto the current value. 2.72, well, I've got an extra 1.72, 172% of my current value from one place to the next to the next. So a percent increase is how much larger that base is than 1, changed into percentage form. It comes out in decimal form. Percent decrease is how much smaller that base of the exponent is, how much smaller that is than 1. So it's always relative to the number 1, because 1 represents that you're keeping 100% or staying constant, multiplying by 1, not doing anything. So growing or shrinking is how far you are from 1, and just convert it into percent form if you're supposed to be answering as a percent. But that, whatever the base is of the exponent, that's called your growth factor, sometimes also called a decay factor, but just generically referred to as growth factor regardless of its size.
It's what you multiply by to get from one value to the next, or to find any value in a function. Sometimes integer numbers aren't the only ones we're concerned about as the x or the exponent values. So looking then at the question on the other side here, not such nice numbers. We have no value for x equals 0. Unlike this one, we had x equals 0, 1, 2, 3. And it's really easy to see what we multiply by or divide by since it's things we know those multiples. So what about something like number 8, where we don't? This is what gets a little messier, but generally we need to figure out two things: where to start from and what to multiply by. If we're saying this is an exponential function, something I'm going to model with a function similar to this f of x that's there, I want to know, well, how do I do that? Now, it's possible to write all of this out without grabbing a calculator, just write it in terms of the numbers that we see. If you want to check to make sure it is actually fitting an exponential function, we need to check and see that dividing the value at x equals 2 and x equals 1 gives us the same result as if we divide 3 versus 2. And then, well, we can kind of, once we get a function, we can check and see that the value when x equals 8 fits in the same pattern to make sure. But I will just say, other than to rounding, because you can see when you multiply or divide by decimals repeatedly, you get really unpleasant decimals, generally speaking. So other than rounding, these do fit an exponential pattern. If we want to write it, we need to know what to multiply by to get from one to the next. So first of all, is this growing or shrinking? Is this an increasing or decreasing function as x increases? Yeah, this one's increasing. It's like 260, 299, 343, and we skipped a bunch of x values, so that's why it jumped up suddenly. So supposedly we're multiplying by something. 260 times something makes 299. I don't know what to multiply 260 by to get 299 off the top of my head, unlike 16 to 4 to 1. It's like, oh, that's divide by 4 or multiply by 0.25. But we know how to compute it. Let me just write this in here. I'm just going to reuse this as long as I already have it. So I'm not going to know this value right away. We can actually write something there without knowing the normal looking value of it. We'll get to that in a minute. I'm going to write question marks there for a second. But what I want to multiply by, well, what do I multiply to turn 260 into 299? I don't know, but I can divide to figure it out, right? Take the later one divided by the earlier one, 299 over 260, which should be the same as 343.85 over 299, that 1 unit growth factor, to figure out what do I multiply to get from A to B, do B divided by A. So I can just say, all right, not pleasant here, but let's see, let me grab where's my equation? Oh, come on. Where is it on here? There we go. Ooh, that got fancy real fast. I'm just gonna delete that, never mind. All right, so g of x equals something. And then the factor that I'm gonna need to multiply is, well, it's whatever 290 over 266 is. I don't know what that is off the top of my head. We could divide it out, or I could just write it like that. But I know that this thing, this fraction, which has ugly parentheses because I'm impatient with this equation editor, that's the thing that I want to raise to the x power. I'm going to do this the messy way. Copy and paste because it's stubborn. There we go. So that is an exponent of x on that, despite the fact that it's outsized. So whatever 290 over 266 is, so, and by the way, iMath issues with rounding, you can avoid them by just doing this way. I know that this is 1 point something, so it's certainly not doubled. It's multiplying by something between 1 and 2 to get from 266 to 290. And we can figure out what it is by doing the division and getting a decimal. It's easier to see that way. But what we have to do now is figure out, well, what on earth is that number at the beginning then? So how do I get the value when x is 0? Because it's not in the table this time. Because I have to start there and multiply by this. There's a couple of different ways we can do it. It's like, well, we know going forward we're multiplying by something to get from number to number to number. Well, not to this one. We'd have to skip a few. So I could just go backwards one. I just have x equals 1. If I want to know x equals 0, if going forward I multiply by 290 over 266, 1 point something. To go backwards, I could divide by 290 over 266. I'm going to work out what that is for right now that we've seen it. 290 over 266 is about 1.09. It's really close to 1.09, so I'm just going to write 1.09 to save us some headaches here. So approximately 9% growth, approximately 1.09. If you're doing this in iMath, you might want to leave some more decimal places of value on that accuracy. But if I need to go backward then to get when x equals 0, I need to divide by 1.09, right? So let me just write that in here. Let's see if I can get to my fraction. I have 260. I want to go backwards 1 unit, so I'm going to divide by 1.09, right? And that's what you could do it in a calculator and get a nice looking decimal value instead of that. The reason I wanted to point this out is exponent rolls. This is something that you do with linear functions much more easily, like point slope form. We don't have the beginning, we just have some other random point. If you look at this, notice that 1.09 is in this expression twice. Once to the x power and once in the denominator to the first power. This expression right here is the same as, well, if I had an x power and a -1 power, I can combine those like this. Well, 260. There. That's the same as 260 divided by 1.09 and times 1.09 x times. Or in other words, we can think of this kind of like, if this were a linear function, you're like, all right, my slope is, whatever it is, my slope's like 30 units or something here. Or is it 39? Between the first 2 points. It's not a constant slope, because this isn't actually linear. But, okay, my slope is 39, and then I have a point 1, 260. So I'm going to do 260 plus 39 times x minus 1. X minus the x coordinate. Here's that same thing. Here's that same x minus 1. So start at 260 and multiply by 1.09, 1 time fewer than what x value you want to find the y value for. So you can do that same sort of, well, shift it around, just kind of adjust by a factor. Same thing as that point slope form. So you can write I could have written this all out without grabbing a calculator and getting that 1.09. It's just a lot easier to see in this format, dividing by 1.09 and multiplying by 1.09 than with weird fractions. But if you check this against that table of values, it should work similarly to if you did 260 divided by that 1.09 and wrote out that decimal in the front. It's just algebraically equivalent expressions for the same thing. I just did want to point out this because it is pretty similar to something you've done with linear equations for years and maybe didn't think about trying it here. So speaking of linear equations, since it's always good to practice with writing those, I've got there's actually 10 functions we're going to write on here. I'm going to pull up a copy of this on the front board too. And what I'd like you to do, take a look at this. It's just as an example of something I can use over and over again. write a linear function, f of x, that models each of those. And then you'll see on the right next to each of them, and we'll do these together, the right half of this, and talk about it a little bit. But take a peek. The right half, the 1b through 5b. Yeah.
So on the last example we just did, there was x minus 1, but the growth 1.09, is that still a 9% growth even if it's x minus 1 and it's x minus 1?
Mm-hmm. It is, yep. Yeah, so 1b through 5b are all about equal percentage changes from one year to the next to the next. But each of these has different given starting information. The numbers are a little bit from one problem to the next, but they're fairly equal from A to B, so that we can make some comparisons about how to write these. Some of these are more challenging than others on both halves of the piece of paper. I'm guessing that you probably have more practice with the A half, and maybe the first ones from B we can do pretty easily, having just worked on these, but we're going to work on all of them so that you become proficient at doing these either ways, maybe see how they're kind of similar. The trick to a lot of math is figure out how something new is related to something old that you already know how to do. That way it doesn't seem as weird. Oh, it's under these, the column A is assuming you're getting the same dollar, yeah. So some of them have the exact same expression, but. So then column A is under the assumption of equal dollars added each year to your salary. Column B is under the assumption of equal percentage change, percentage change from year to year. And I'll post a copy of this on Canvas under the list of miscellaneous paperwork that I've handed out in class, or documents I've used that aren't part of your textbook. All right, let's talk about the column A ones. So in terms of like level of difficulty, I tried to make these so that it's like easiest at the top and got harder as you go down, but after a while it's like, which one of these is harder? Depends on which sort of thing you like doing better, I guess. But 1A is maybe a sort of question that you saw earliest in your math formula writing life. If we're writing a linear equation and I know a y-intercept and a slope, essentially, just pop them in and I'm set to go. But again, we're starting at 25,000 and going up by 2,000 per year. So if I were going to write a function for this, f of x, I wish I wouldn't auto-capitalize because that annoys me, equals, I'm just going to write it in the order I said it. Start at 25,000 and add 2,000 per year for x years, right? Now we're probably only interested in whole number values of x, not like 2.82 years because you're not getting raises in the middle of the year. But regardless, we could use this function's output values for whole numbers of x to represent your salary after having been at the job for x years. So compared to number 2a, what is it that I need to do differently, or I have to do a little bit more in order to write my function for number 2a? Well, it's still f of x equals start at 25,000, but it doesn't give me the amount of the raise. So how do I find it? Maybe seems like an easy question, but how do I find the amount of the raise from the given information?
Subtract year 1 from the principal.
Yeah, subtract year after year 1 from this, and minus the starting values. 27.5 minus 25. So that's 2,500. And if we're, again, under the assumption we're getting equal dollar amount raises each year, then the fact that those are different by $2,500 means that's apparently what my annual raise is, $2,500 per year for X years. Now, I'm going to skip over to the B column. I know I asked you to do all of column A first. But comparatively speaking, we have the same sorts of information needed for these problems, kind of, for 1B versus 2B, just like 1A versus 2A. They both give us a starting amount. Part B tells us how much we change each year. We have to do a little bit of figuring to write the function, as we found. 2B tells us the salary after a year. So we're going to have to compute how much it changes. In this case, it was subtraction to get the yearly raises. So in question 1B, again, we started at 25,000, and we're getting a 2% raise each year. So instead of adding to get this is our, it's always a percentage of that number, or a percentage of a result of having used that number, which involves multiplication, right? These percentage. So what is it that I'm going to multiply by to get the first year's salary in one step? To do a 2% raise or a 2% increase? 1.02. Now that's a very small raise, but that would give us the first year's salary, right? If I wanted the second year's salary, I'd multiply by 1.02 again. Third year's salary, I multiply by 1.02 yet again, and so on and so on. So I just need to, let me do this the non-equation editor way. Where's my exponent thing? There we go. 25,000 times 1.02 to the x. So we just converted this percent change, which was a growth, percent growth, increased by 2%, phrase 2% raise, changed into multiplication by 1.02. This number is 0.02 different from, 0.02 larger than the number 1. So multiplying by it makes our result 2% larger than it used to be. All right, so for 2b, again, we're missing the percent growth that we supposedly have. We have to compute it, but the function starts out the same. F of x equals 25,000 times something raised to the x power. That's going to be our function structure. I just need to know what percent change I have and then convert that into my growth factor. Or, since I don't have a percent listed, I don't have to find a percent and then convert it. How can I find that growth factor from the numbers that are here? Yeah, just divide. So when we were adding over and over again and I needed to figure out, well, how much did I add? I subtract to get that. When I'm multiplying over and over again and I need to know, well, what am I multiplying by? I divide to find that. It's just the inverse operations. 27,500 divided by 2,500 should come out pretty nicely, right? Yeah. 27,500 divided by 25,000 is 1.1. That's our growth factor. What percent increase does that mean, by the way? 10%, right? That's a 10% raise per year. Or you can maybe see, oh yeah, it increased by 2,500. 2,500 compared to 25,000. It's just off by one digit. It's off by a zero. So it's 10% of the original. But you can get that all in one. Again, we did division. Division. To get the yearly raise percentage, which is not precisely true. It'd be the yearly growth factor, the number that actually goes into the equation. If you want to convert that back into percent raise, we can say, okay, so the part in excess of 1, 0.1, is the decimal equivalent of our percent raise. So this is a 10% raise. All right, so let's look at some of these later ones. Let's see, number 3, part A. Well, they say the exact same thing, but the left column is equal dollar amount raises, and the right column is equal percent raises, which is, we've had less experience with, but on the right-hand side, or the left-hand side here, again, we start with 25,000, we're getting equal dollar amount raises per year. So I can say f of x equals, what would I do for this one? 25,000 plus, yeah, 2,000x. How do you get 2,000? How do we know we have $2,000 per year raises? Where's that 2,000 come from? That's right.
31,000 minus principal, and then what's left divided by 3.
Right. Like y2 minus y1 over x2 minus x1. Only x1 is 0. It's a starting salary of 25,000 and 3-year salary of 31,000. So it's kind of like we have a chart with two numbers in it, 0, 25,000, 3, 31,000. If you want to know the raise per year, total raise divided by 3. Since it was added on, we added on something 3 times, we had to have added on 2,000 3 times in order to get from 25 to 31,000. So again, we did division to split up adding something 3 times, or if I wanted to think of an algebra equation here, I'd say like, well, 25,000 plus something 3 times has to equal 31,000. And I can solve for x. I don't want to call it x, let me call it r for the amount of the raise. And we can say, oh yeah, my raise was 2,000 per year by solving that. And why I say that is, let's look over here. I'm still starting at 25,000. I want to multiply by something over and over again, so that after using it 3 times, I get 31,000. Kind of eyeballing this one's harder than the linear equations. It's a harder function structure. And this isn't something you've had homework already do about, your upcoming homework assignments use this idea. But if I have to multiply by something,
Isn't it like x to the cube power equals 25k?
yeah, so I have a,
31.
right, yeah, so something, I need to multiply by this 3 times to get 31,000, right? So 3 years, 25,000 times, I'm gonna say R, times something to the 3rd power. Exponent yourself, has to equal that 31,000, right? So I'm starting at 25,000, I'm getting raises 3 times. I'm just using R to indicate, in this case, that growth factor that's representative of our yearly raise. If I want to know how much my raise is, it's gonna involve a cube root. Now, we didn't write out all of that previously. We did division to get this yearly growth factor, because we had consecutive years, 27,000 divided by 25,000. If I were to have written something like this for the previous question, that cubed wouldn't have been there. It would have been a 1st power. That's why it was just division last time. So I can find that growth factor over 3 years immediately. I can just do 31,000 divided by 25,000. And I don't know what that is. 1 point something. Divided by 25,000, 1.24. That's a 24% raise cumulatively over 3 years. Now, that does not mean we get 8% per year, because this is 24% all of one number, but 8% of 3 different numbers wouldn't be the same. So if I want to get, well, how much does this work out to per year? I'm not going to divide again. We have to do a cube root. Or I've done the first step of solving this equation. I figured out what R cubed is. Using my 1 year growth factor 3 times has the effect of multiplying by 1.24. But what I want to know is, well, how much is this per year? So we did the division. Now I have to take the cube root to get my 1 year growth factor if I want to write it in there. Now, there's 2 ways I could do this. I could write the 1 year growth factor, or I could not. But 1.24 is not the answer I want to write in this function. 1.24 is R cubed. So I need to take a cube root of that. I happen to have a cube root button here, so I'm going to click it. It's about 1.074. 1.074, approximately. Now, if I wanted to write it exactly and avoid round off error and iMath AS marking your answer wrong because you just of rounding, another way you could write this, f of x equals 25,000 times, well, how did we get that 1.074? We took our much nicer number. I mean, we could even go as far as 31,000 over 25,000. But it was a nice round 1.24. Came out exactly. I know that's not rounded. Now, that number I took a cube root of, right? Cube root is the same as what power? 1/3 power. I'm going to write it this way. And then we raise that whole thing. I'm just using brackets to emphasize which matches with what. If you're typing something in iMath, just use parentheses. But, so I've got 1.24 to the 1/3 power. That's where that 1.074 came from. It is the cube root of 1.24, which was exact. By taking the cube root, it was not a very nice number anymore. But this would be the same, all right? And exponent rules, if I want to write this without double brackets parentheses situation here, I can even do a little algebra and clean that up a bit and call this 25,000 times 1.24 to the, what do you do if you have 2 powers on the same number like that? An exponential expression raised to another power. Multiply the exponents? Does that sound familiar? Like 2 cubed to the 5th power
is 2 to the, multiply 3 and 5, 15th power.
Well, this is a 1/3 and an x, but that's the same as the x over 3 power. So I could also do this. I had a 3-year growth factor, this 1.24. If I take a cube root, 1/3 power, now I have a 1-year growth factor. I can either write it with that 1-year growth factor, like solved all the way for r, written in place, or I can not deal with the actually doing the cube root and rounding and just put the cube root into the function. Kind of the same way we did the -1 in the previous expression. We just had this little adjustment that we had to do. There's a variety of ways to take care of these, to clean them up. They're all equivalent other than rounding. So avoiding rounding is good if you need to use a function over and over again. But if we get the general idea, that's what I want you to see. So dividing by 3 doesn't always come out evenly also. In this case, dividing by 6,000 by 3, that worked out nicely. If it had been something that didn't divide out nicely and we had like 0.33333333, you might have wanted to do the same thing, like leave it in a fraction instead of write out the decimal. But it would just be a fractional number here, like, what was it, 6,000 over 3, writing something like that. So division by 3 versus cube root is the difference between linear and exponential here. All right, so 4 and 5 are a bit more challenging, but the ideas in the A sections, it's just I have different information. So for 4, we have a salary. We don't have the starting salary, but we do have the yearly raises at least, so that's nice. But not having the starting salary, we have a year 5 salary instead. I don't have to work backwards and figure out the starting salary. I can, obviously, right? We could solve backwards to find what's the salary at year 0, but you don't have to. We have point slope form that takes care of that. We had our f of x. Well, we're starting at 35,000. Oops. Not at the beginning of everything, if I can type properly. Not at the beginning of everything, but eventually. And I'm adding 2,000 a year. But if x is representative of how many years you've been on the job, I'm not going to add, like, if I just left it like this would indicate starting at year 0, I had $35,000. We do that x minus x1. Remember our point slope form? Initial y value plus m times x minus whatever initial x value you have, x minus x1 or xi. You can move this to the end if you want, if you don't like it at the beginning. But if we're starting at some initial point that isn't necessarily 0 comma something, not necessarily the vertical intercept, all we have to do is just adjust for that. This was a 5-year salary for that 35,000, as opposed to a 0-year starting salary. So just a slight adjustment, and we get to make the same adjustment in part B, which is very similar. This part B is just like the one that we did earlier. Well, if we have this f of x equals 35,000 times, 2% raise. That's just like part A, 1.02 to the something power. It's not just x, because that would indicate that, year 0, I have a $35,000 salary. Guess what my exponent's going to be? Yeah, x minus 5. Or, alternatively, you could solve for what the year 0 salary is by taking this 35,000 and dividing by 1.02 5 times to work backward. But that's what that minus 5 in the exponent is doing. It's the equivalent of having 5 factors of 1.02 in the denominator, a negative 5 exponent. making it 5 factors of 1.02 smaller than it would be were that negative 5 not there. So this is just that equivalent of, oh, this point slope form like that, I wasn't starting at 0, I was starting someplace else. So the last questions here, neither one is particularly easy. Person has a salary of $35,000 after 5 years and $41,000 after 8 years. If it's equal yearly raises, that works out to the same yearly raise as the last two questions, $2,000 a year. All right, so that's $6,000 between years 5 and years 8. Just that sort of, find the slope, or increased by $6,000 over 3 years. So that's $2,000 per year if we're going with equal yearly raises. So that's the same increase as before. F of x is, well, we'll say we're starting with $35,000 and adding $2,000 per year. It's just that we're not starting for real at $35,000. We're starting 5 years earlier than the year that we made $35,000. So same x minus 5 as the number 4. This was our year 5 salary. We could work backwards 5 years to find our starting salary. If it's $2,000 a year, just subtract and work backwards. That's not too hard. That's $25,000 again, right? So it's really the same as the very first problem, 1A. Just in a different form because we had different information. You don't have to simplify to a specific form. 5B, and this one's not going to be the same as anything. But I can say, well, I'm starting with 35,000. I don't know what I'm multiplying by something. After 3 years, I know that worked out to a $6,000 raise, but I don't care about the dollars. I need to know the percentage. So we have to do this dividing thing, and that's going to help us find what goes here. It is over a period of 3 years, so we could do the same cube root like we did in a couple problems ago to figure out from a 3-year growth factor to a 1 year. But in order to do anything with this, let's see if this is a nice number. 41,000 divided by 35,000. How much of a raise did I get percentage-wise in those 3 years that are shown? Not a nice number. But for purposes of brevity here, I'm going to call this about 1.17. What was the third digit? 1? So it's about 1.171. That's 3 years of growth factor. So if I multiply by 1.171 repeatedly, I'm going to get 3-year chunks of raises at a time. So I don't really want that. I want a third of that as a factor, meaning I want to take the cube root of it and then raise that to the x power, which you can write as the x over 3 power instead of doing that as 2 steps. But again, that's, if you don't like seeing that, like I'm not going to know where this x over 3 came from, that's weird. You can write it in a couple of steps. Again, I'm just using brackets to emphasize what goes with what here. But cube root of that would be our 1-year growth factor, so that I can have just x as this. All right, put in 1 year, 2 years, 3 years, etc. Now, the only other thing that I need here is because this would say that my starting salary is 35,000. And it's not starting, that's after 5 years. So what else do I need on my x here? Go back 5 years, just like the previous question. So in reality, and making that adjustment, if we have this all as one exponent, it'd be x minus 5, whole thing, over 3. So that cube root gives us the 1-year growth factor. We want to use that over and over and over again. And again, this minus 5 here, I could also divide by the cube root of 1.171 5 times, or put that as the fifth power in the denominator, it all looks really ugly. This would be the most succinct way to write it, not easy. This is probably harder than any question you're going to run across on your test or quizzes or homework. This is kind of like everything that could potentially come at you at once. We don't have the growth factor, it's not a nice number. We didn't have year 0, and it's hard to compute backwards because it wasn't a nice number. So everything's kind of wrong with this in terms of the information given. None of it's easy to use. But it's really just a combination of all the different things from the previous steps. So I want you to have this. I'm going to post a copy of it if you want to like try it again later from scratch and see if you can come up with some way. There are multiple ways to write anything that I wrote on here. I was just kind of doing this, the starting value, and then how do I change away from that method, as opposed to a specific format like slope intercept, or maybe a point slope form that you like to use for the linear. And with these, there's other ways to write because of so many exponent rules. There's many equivalent looking ways, or equivalent value ways that look very different. But in terms of these growth factors, n unit growth factors, all that's saying is like, so if I have something that's a growth factor that doesn't pertain to 1 year, if it pertains to 7 years, I can take the 7th root of that number to figure out what happens over 1 year. Or if I want to find even a smaller interval, if I want to figure out what happens over half a year, I could take the square root of that, because half a year compared to a year is half the size. So if you need to convert these, it's doing roots or multiplying if you need to go bigger. If I have a 1 unit growth factor, 1.02, and I want to know, well, what percent does it change by over 5 years? Maybe I'm only interested in years 5, 10, 15, 20. I could work out 1.02 to the 5th power and use that number and talk about that percent change over 5-year intervals. 1.02 to the 5th power is not the same as 1.01, or 1.1 rather. I don't know what it is, but I want to know now. 1.02 to the 5th power is 1.104. So 2% raise for 5 consecutive years isn't exactly a 10% raise, it's a 10.408% raise, approximately. It's that number, minus the 1 is the percent change. So by just taking that growth factor, the factor that shows up, the 1 point something or the 0.82, like whether it's growth or decrease, and raising that to powers or taking roots of that to get smaller intervals, you can get growth factors over different periods of time other than just 1 year or just what you happen to be given. So, that said, I have for you in iMath, there's a quiz, which is available now. Here, let me put this in the less messy student version. And it is due by noon today. We've got about 20 minutes to work on it now. It's like, I forget, 5 questions. It's not extremely long. You might be able to finish it entirely in class with no problem. Maybe it'll be almost done, but it's not timed other than it's just due at noon. But while you're in here, you can work on it. You can work with one another if you'd like to. You can compare notes, ask around. If you're having difficulty, I could maybe give you a hint. But if you have a device with you, whether it's a phone or a laptop, you should be able to work on this. Like I said, it's fairly short, and that is due by noon. So it's about growth factors and writing exponential functions. And it's not timed. You can put